Great. Thank you, everybody, for coming. So the giant leap in deep learning research in recent years have led to a massive adaptation in deep learning in various industries. Okay? Going from research to production is a massive challenge, as we all know it, especially in the automotive industry, right? Where, in my opinion, the two main challenges there, the biggest challenges, are accuracy and runtime performance. So throughout this talk, I will share, from my experience, the difficulties that you, perhaps some of you, but you will all encounter eventually when you actually try to fit these deep learning algorithms into hardware, specifically into automotive hardware, and share from my experience at Brodmann17 how we actually tackle these problems. So our vehicles are becoming smarter, and by smarter, I mean we're adding automated driving functionalities into them. The main reason for adding these functionalities are, of course, regulation. They are a competitive edge for automakers, and of course, the buyers need that. They are actually excited about adding this technology. The cost of adding this sophisticated capability is that the underlying algorithms are also becoming complex. And specifically, the deep learning, which are, as we all know it, compute hungry, right? So if we look at the levels of ADAS autonomy, so if we start from going from level 0, which we have there, for instance, regular cruise control, which is a fairly simple algorithm, which you can actually implement on a very low-power processor, going through adaptive cruise control and then to an autopilot, which is level 2, you can imagine the dramatic effect it has on the underlying complexity. Okay, so the complexity increase does not happen only because of the increase in the requirements, but also because you would like to support different scenarios. And the scene complexity will become higher and higher, not only in terms of scene appearance. So for instance, instead of dealing only with clear weather, you would also like to handle stormy weather, but also scene dynamics, like what are the objects in the scene and what is their behavior. And we heard a lecture about that previously. So this complexity is rising, okay? And it will increase to rise. As we all expected, we still don't know exactly what will be even the final scheme for instance, for level 4 algorithms, but you can predict that it will increase. So if we look specifically on an example of computer vision for deep learning, so for instance, on the left, you might imagine that's the requirements from a computer vision algorithm working on, let's say, a level 1. Functionality, for instance, fault collision warning. So there you need a single object from a single class. Perhaps only a 2D bounding box would be enough. And of course, you would restrict it to be at this top performance only on specific scenarios. So perhaps you'd slack the requirements at more difficult scenarios like darker environments, stormy weather, and so on. And on the right, you have a much more complicated scenario in which you have many different objects. Perhaps you'd also need 3D bounding box detection, perhaps free space segmentation, and so on. So all of these is required in order to meet the target functionality. And what we do basically, and what most companies do in the labs, they also increase the complexity of the algorithms. So in order for the deep learning algorithms to support these kinds of advanced functionalities and the vast amount of corner cases they actually have to deal with, they will use larger and larger, more complex algorithms and perhaps numerous algorithms. But where do we actually see these algorithms today? Okay, so where do we have deep learning algorithms today? We have them mostly in the premium cars, right? Premium car models, and on the right you see some examples. They recently introduced a Tesla FSD, which has actually 144 teraflops with 100 watt of power consumption, and NVIDIA Pegasus 320 teraflops and 500 watts And this, I guess, the requirements from this hardware will only increase because, as we mentioned, the complexity is rising of the algorithms, and we still don't know exactly how to plan for the final product, and it will take time. But as a very sharp contrast, what we have today and in the near future, when we're talking about close to being a mass production, we have much lower processing power. So if we go from left to right, so we see a lot of ARM processors either as part of automotive grade hardware or aftermarket devices. So these have a range of 57, 6 Gigamax NXP S32V, TI, TDA, and Renaissance. So they have around 100, 150 Gigamax. So these are actually 3 orders of magnitude weaker than the previously presented processors. So there is actually a very large gap there. Okay, so bridging the gap, when I wrote here bridging the gap, it's not necessarily bridging the gap of how to put deep learning algorithms into today or near processor or near future processors. So it's basically how to utilize the hardware to the extent. So you would like to add more and more functionality to any platform, no matter whether it's weak or strong, because cost consideration, time consideration, you would like to optimize this part. So let's see how to tackle this problem. So reviewing the deep learning stack, and we are all familiar with. So I've already reviewed the hardware. So we have CPUs, GPUs, DSPs, dedicated accelerators, which will be becoming more and more common. On top of them, we have the engines, right? So we have the deep learning engines. So if we consider TI, so we have the TIDL, TensorRT, ARM compute library, and the primitive libraries. So these are actually building blocks that allows you to utilize the hardware in an optimal manner. So basically, they are a must, and they will allow you to utilize the hardware as it was meant to perform. On top of them, you have the deep learning frameworks, which actually allows you to perform the research. They are not intended to run it at inference time. And on top, you have the algorithms. So you wouldn't be surprised if I'll say that I think that the algorithms are the crucial component in figuring that out. So bringing these AI or deep learning algorithms into mass production. So let's start drilling down. So when you consider the typical deep learning development cycle, and later on I'll show you how I think the cycle should actually look like. So you choose a model. So for instance, you choose a YOLO. You collect your training data, which has to be labeled. You crunch some numbers on a very high-end GPU, which is in most cases not even close in terms of the amount of computation it allows you to the final target hardware. So this is actually, I think, this is the first. So this is where the problem actually starts in most cases, because you either postpone the problem of running on the target device, or you basically avoiding it. Okay, so but you will encounter it eventually. So you have an inference model, and you actually want to deploy it. In many cases, you get stuck, right? So you have, let's say, you have an algorithm which runs with I don't know, 2 tera operations, 3, 4, and you actually want to deploy it on a Renaissance. So how are you going to do that? So in many cases, you actually, as I will show, you're in a big trouble, right? But in some cases, you might be able to optimize the algorithm, and I will go through some common optimization approaches. I guess many of you who deal with algorithms are currently taking, and a bit more advanced, and I will end with what we do at Brodmann17. So the first one, which is pretty straightforward. So if I gave a similar talk about a year and a half ago, and And then we actually had some thoughts about using perhaps less than 8 bits. So we're talking about reducing the bit precision. So I think today it's pretty common that you can go down up to 8 bits. Okay, so lowering the bit precision in inference is actually giving you these advantages. It's able to speed up the inference, reduce the memory bandwidth, and also reduce the power consumption. And the reason we can do that is because neural networks are basically robust to small changes. So we're not talking about classical computer vision algorithms. Deep learning actually has a much larger robustness. The activations are limited to a narrow range, and actually they are supported. Using 8-bit quantization is actually supported in most neural network inference engine. On the right, you can see an example. This slide is when we actually exported one of our algorithms into CPU processors. So some of them are able to use the 8-bit instructions better than others, but you should expect to see the gains we see there. So this is common. You won't lose any accuracy there, but you will not get a few orders of magnitude of improvement there. Another technique, which kind of an engineering optimization, is introducing the speed accuracy trade-off. So the common trade-off you might think and are very common when trying to deploy deep learning algorithms today is basically using faster algorithms like YOLO, reducing the input resolution of the image, or using a smaller backbone. So you see the graph on the top. You can see the rightmost corner. It's the most accurate neural network, or basically a neural network algorithm, using the largest backbone and largest input resolution. And in the lower left part, you'll see faster algorithms, reducing the input resolution, and using a smaller backbone. So I guess for automotive, these kinds of trade-offs in many scenarios are a big no-no. And using this kind of techniques, you will be able to get some gain, but it will not be very large. Reducing the network size. So this is pretty common. We all read a lot of academic papers talking about pruning. So pruning is the process of taking an already trained neural network and reducing its size by eliminating neural connections or complete filters out of the network, which is also named structured pruning. So you select which neurons, which layers you would like to remove using some heuristics. For instance, the layers with the least, with the smallest activation magnitude, and you omit them. You need to retrain the network in order to regain the lost accuracy, and you actually go on. So this is a highly sensitive process. Anyone who's ever tried to prune a network knows that first it's a highly sensitive process. There is a recent paper in the recent iClear conference actually comparing pruning neural network or successful pruning neural networks of winning the lottery. So you should read this paper. It's actually really good. So it's highly sensitive process. But the gain is very, very limited. The research papers, most of them are talking about, they're starting from a very high, very redundant networks like VGG16 and so on, and the results they get are actually amazing. They actually are able to reduce them by a factor of around 10. But if you already start from a very optimal neural network, like we do in Brodmann, so you would actually expect to see a very small gain. And this is a figure showing one of our experiments. Okay, so we have a baseline model. We prune that, and we continue to prune it and continue to prune it until we reach the point where we actually manage to get twice the performance, but the accuracy dropped by 75%. So you can actually cannot utilize this kind of techniques, and it's actually pretty it's intuitive, in my opinion, because you're starting from something which is already trained, something you already designed, and you're trying to adapt it. Okay, so adaptations by nature will only give you minor changes. A more advanced techniques. A recently published paper called NetAdapt is taking a much more interesting approach, which I will elaborate moving forward, is to perform the pruning, but take into consideration the target platform. Okay, now that makes a much more sense because, as we all know it, different hardware platform and different software or inference implementation have different reactions with different network architecture. So you'd actually would like to know what your final network, which you are training, what will be the runtime or what will be the memory consumption on the target platform. And this is completely different from the typical ordinary training process, which I've shown in the beginning, of training a neural network in the cloud without taking into consideration the target platform. So this is, I think, a very important point, which is being touched by many recent papers, and I think it will start to catch up momentum, and a lot more papers will start dealing with this problem. So you prune the network, you benchmark empirically on the target platform, and then you redo it until you reach the final KPI. In one of their experiments, they actually showed they were able to improve by a factor of 70%. Okay, and that's pretty nice. So, as I mentioned, adaptation has its limits. So why don't we take it to the next level? Okay, so many new approaches are talking about neural architecture search. Google has a very famous paper about that. NAS, they continued with a more efficient version of doing that called ENAS. Then for mobile targeted devices, MNASnet. So the motivation is, instead of doing adaptations, so completely invent a new network, a new architecture. Instead of doing the manual design, do it completely automatic. So that was the inspiration. They also phrased the frame AutoML, and we'll talk about what exactly is AutoML next. And if you're already doing that, so why don't you take into consideration the target platform? So all of these approaches, all of these papers, and I strongly suggest you read all of these papers and many more that are very interesting. So the key discussions and key differentiation factors within them are, I think, in my opinion, are what I wrote below. So what is the possible search space? So theoretically, you cannot search the entire space of neural networks, right? So you have to limit the space in terms of, that's a practical reason, but it also has an applicative implications, how to represent the search problem. Some of them use reinforcement learning, some of them use recurrent neural networks, some of them use evolution. Are you going to target hardware? And if you are going to target hardware, how do you do it practically? Because if you train and need to evaluate on a target platform, you need to actually invent something in order to be able to gap that, because when you train on the cloud, it's a very fast process. Porting to the hardware, getting the feedback back, it will limit you. So you need to think of ways to do that. So they invented proxies, and there is also a paper about proxyless NAS, training, doing NAS less than 4 hours. It's an interesting paper. And so is it a real AutoML or not? So basically, if we see the evolution of neural architecture cells going from V1 to V3, which is the latest version, we can see the gain is reducing. And a lot of the gain is actually being made by making manual design choices. So AutoML is not necessarily AutoML, and the key and a very big component, a very critical, is your past knowledge, your previous generation of neural networks, and the design principle you manually decide. Okay? And this is actually one of the key things we do at Brodmann17. We actually invented our own design principle based on weight sharing, computation sharing, which actually allows us to get a very big accuracy and very, very tiny amount of computations. So taking the design principles, you need to, especially if you're working in the automotive industry, you need to have a workflow, how to train these algorithms, not a one-time process. You need to think of an iterative process, getting the new feature definition, collecting the data, and the data collection is something actually alive. You start training in our training platform. You do the search based on the design principles I've earlier mentioned. You export to the embedded platform. While you're doing the training, you get this feedback, and the iterations goes on and on until you reach the final production model. In order to be able to orchestrate such an operation, so you're talking about a search problem, you might think of thousands of different trainings going simultaneously. You need to orchestrate them, you need to synchronize them, you need to export to the final hardware. We had to actually develop our own system to do that, so cloud-based system, which allows us to do the search, the training process optimization, and so on. Over here, I show you a small, a very short illustration of a process, a real process we did. So we're starting from an existing model, or basically an existing design of a model, and we start from around 80% accuracy. The target in this process, and you can actually determine the target any way you want to, so the KPI is user-defined. So the target was keep the same latency but improve the accuracy, and within 2 days we were actually able to improve the accuracy by 16%, almost 16%, and it took us only 2 days. So neural architecture search, even if it's not automatic or fully automatic, it's still semi-automatic, and you still need to have these design principles, manual design principles incorporated, have a very large applicative implications, because they allow you to utilize your research power much more efficiently. And I'm concluding, so the key takeaways I want you to take from this talk are the increasing automotive functionalities are also increasing the algorithm's complexity. Current optimization techniques are limited. So you either have to wait for the next generation of hardware, or you actually need to think of how to develop efficient algorithms in order to utilize existing and future hardware, and this is what we do at Brodmann17. I invite you all to see our demos. We have some nice demos working on ARM processors. And that's it. Thank you very much.